All right, off we go. So, today is about randomized rounding. Um, damn. My usual recap was the magic of copy and paste. So our first lecture again was about linearity of expectation. Our second lecture was about heavy hitters and introducing hash functions and Markov's inequality. We then put hash tables on steroids with linear probing, and also put Markov's inequality on steroids with this k-wise independent stuff. Lecture 4 was about the random contractions and having some fun graph algorithms for minimum cut. And last lecture was about random graphs and the giant component. But it introduced and maybe offers some perspective on the Chernoff bound, which time permitting will be relevant today as well. It'll be relevant every class. So today it's not clear that I'm going to introduce any new particularly probabilistic thing. Like, there's no new inequality today, but maybe as a more general technique, we're going to be focusing on doing approximation algorithms based on linear programming and randomized rounding. That's the general technique of the day. The problems we'll look at are maxadd as usual, sec cover, and covering integer programs just as a generalization of sec cover. So let's start with just a high-level overview of this LP approach. Okay, so today is a story of sort of two things. One is, of course, what we talk about a lot, polynomial time solvable things versus things that are NP hard. And, well, we still want to do something about the NP hard problems. So one way to bridge the gap is approximations. Of course, we've done some approximations before, so it's not too new of a concept. And I think one of the themes that'll come out today that are running in parallel is the idea that, we're often interested in discrete optimization problems, at least in this class, which unfortunately tend to be NP hard, whereas continuous optimization problems are generally solvable. Okay. So at some level, we have sort of oracle access to this kind of problem, but we're really interested in this kind of problem. And we'll see randomization playing a role to help us sort of connect these two areas at the high level. So those are the big ideas. Okay, so let me introduce integer programs. They're about as dry as they look. Okay, so this is sort of a canonical, discrete mathematical program. So let me go through the parts. So I'll start with the second row, which is the variables. So I have a vector x consisting of n integers. Okay, so a vector notation. So it's really x1 through xn, each of which are required to be an integer. So the mathematical program is somehow choosing x as integers to optimize something. What is it optimizing? Well, in this case, it's, let's say, minimizing or maximizing or something. The sum of Cj times Xj. Okay, where Cj is some input parameters for the problem. So we'll look at problems today that are minimizing Cj times Xj, in which case Cj might be interpreted as like a cost of taking an item. And Xj is how many of item j you're taking. And we're going to do constrained problems as usual, but they're only of a limited type. They're ones that are specified by linear equations. Okay, so I wrote this in matrix notation, but if I were to expand out, one of these, this might look like a bunch of the sum over j of aij xj is less than equal to bi for, a bunch of different rows I. Okay, so one kind of constraint saying, okay, you can only take so much of x's because, the sum of the ai's is too big, that's bad. But we can also have equality versions, and we can have greater than equal versions. Okay. So the real defining characteristics are, one, we're optimizing over integer values. Okay. And two, basically all of the information, all the constraints, all the objectives, they're all linear functions. They're summing up the xj's and saying, oh, it's less than this, or bigger than this, or equal to this, or minimize or maximize this weighted sum. Okay, so everything is a linear function subject to choosing integer stuff. Okay, so this is a very general thing. This is a very flexible thing. You can walk into your kind of real world scenario of choice and try to model your situation. Consequently, it's easily NP hard. You can take any of your favorite problems, M-dependent set cover, SAT. We'll do some of those today, and model it as an integer program. Okay, yeah. Yeah. So you don't have to have all the kinds of inequalities. It could be any subset of them. It could be only the equalities or only less than equal, and stuff like that. Yeah. In fact, you can write, for example, the equality as less than equal by writing ax less than equal to b and negative ax is less than equal to negative b, and then they would have to be equal. So they're all kind of roughly the same. I just put them all up there so it's easier to see. Okay, so these are hard, but they're useful. These are really what model the kind of discrete optimization problems we're interested in. So the a closely related thing is linear programs, which is going to be just like integer programs in terms of all the input being specified in kind of as linear functions. Okay, the only difference now is that instead of optimizing over integers, x is allowed to take on any continuous value. Okay, so in many ways it's the same thing, but I'm now saying, okay, x can be 0.1, or x1 can be 0.1, or 0.2, or 0.3, or whatever. Okay, so I'm now optimizing over a continuous space rather than a discrete one. That's the only difference. Okay. All right. Okay. Now, unlike integer programs, which are being able to model discrete problems exactly or are very much NP hard, linear programs have polynomial time algorithms, technically weakly polynomial, but that's a secondary thing. So the first kind of real algorithm to solve linear programs was called the Simplex Algorithm in 1947. It's not actually polynomial time, and there's examples where it would take a very long time, but it's very practical. So roughly since 1947, everyone has been okay with the idea of writing a linear program and feeding it to a computer to solve it. The exceptions don't really come up much. That said, getting a polynomial time algorithm was a big open problem for a long time, especially as linear programs became more and more useful. And that was finally resolved in 1979 by something called the ellipsoid algorithm. At least it was resolved on paper. So ellipsoid refers to the John's ellipsoid theorem, so it's a bit mathematical. And then a slightly more practical approach called the interior point algorithm came out in 1984. Okay, so these last two algorithms are polynomial time. So we can at least kind of on paper say, oh, we have polynomial time algorithms to do this and do that. In practice, you would just get the best LP solver you can find off the shelf, which is probably a mix of these hardcore algorithms and a bunch of heuristics to speed up common cases. But the real point is that we can solve linear programs in polynomial time. Going into these algorithms is a whole class unto itself, so we won't do that today or in this class. Okay. So this is how I'm sort of looking at it at a high level. Integer programs represent discrete optimization and things that are NP hard, okay, but maybe I'm ultimately interested in. Linear programs represent continuous optimization, and they're in polynomial time. Okay, so somehow This is what I need. This is what I have. Okay, so the idea of this class is to explore the idea of trying to take advantage of linear programs to approximate integer programs. So I want to solve an integer program, or I want to solve a discrete problem, uh, and I have sort of this very powerful linear program solver as a black box. Okay, so what's this approach going to look like? All right, so we're going to usually start with a combinatorial problem like SAT or setcover or something like that. Step one is to just write it as an integer program. Typically not too hard, but maybe the first couple of times we do it, it might be awkward. Okay, so that's step one. Step two is to take rats. Step two is to take an integer program and turn it into a linear program, which we often do very little beyond just removing the integrality constraint. Okay, sometimes there's opportunities to do or reasons to do more clever things, but not today. Okay, so we'll take our LP and we're just going to plug it into a black box. Okay, all I care is that there's something that can solve it. Okay. Out of this black box comes an optimal solution to the LP, some fractional solution. Okay. Now, I was originally interested in some discrete problem, so somehow we have to figure out how to interpret the fractional solution, or maybe try to use it as like a hint towards an integer solution. And that's really where the work comes in this last step, where somehow I want to take my fractional x and round it to an integer solution z. Okay, and I'll know that x is optimal for the LP, so it always have really good objective value. And the LP is actually kind of easier than the integer program. Any feasible solution for the integer program is feasible for the linear program. Okay? So x will always be really good. The only issue will be that it's fractional. It has like 0.3s, 0.4s and stuff. That's no good for me. But it gives me sort of a basis. If I can find like a vector z that's sort of nearby to x and comparable to x, then I also know it's pretty good overall. That's the high level strategy. Okay, and rounding is today. I mean, there's different ways to do rounding, but probably the most common or most versatile and practical, and the one we'll do today, is randomized rounding. It solves a lot of problems. Any questions about the high level? Great. All right, so we'll just work through a few problems then of this paradigm and try to get a good handle. Yeah, question. Yeah, absolutely. Um, right. So the first problem will almost certainly be NP hard for most of the cases we're interested. So when we turn x into an integer, we'll probably lose something. Our objective value probably won't be as good and stuff like that. We'll have to sacrifice some stuff in exchange for integrality. Okay. Maybe one more thing to point out is that we'll see the rounding algorithm itself is usually pretty simple. Most of the work is in the analysis. So probably the running time bottleneck will be the LP solver in most cases. So it's still polynomial time, and if you have good software, hopefully that won't be an issue either. Yeah. Yeah, yeah. So whatever problem we start with, we want to write it down as an integer program. Yes. Oh, it'll usually be pretty straightforward. Yeah, it should take linear time. But hopefully a couple examples will make that clear. Yeah. Besides, yeah, we're not too worried about getting very fast algorithms either. We're looking at problems that are already NP hard and just focusing on getting it to be polynomial time. I mean, we haven't even discussed the polynomial running time of this thing, which maybe in theory is probably like cubic or something, right? And that's only in theory. So, okay. All right. Um, all right. So my first application was going to be MaxSat, but any questions before we start? Okay, so just to remind us about SAT, I guess this were some slides from before, but you have some formula and we want to try to satisfy as many clauses as possible. And last time we'd analyzed, or not last time, but the first class, it feels like a long time ago, we analyzed this algorithm where we just randomly assigned everything to be true or false. And for 3SAT, that got us a 7/8 approximation, which amazingly is actually best possible for 3SAT. Okay. All right. I guess here was the analysis. Just to remind us, the key was linearity expectation. Okay, so whereas in that class we were doing k-sat or 3SAT, where there's exactly 3 variables per clause, today we're going to look at sort of max-sat without the k, meaning each clause can have any number of variables, 3, 4, 5, or 1 or 2. That's the only difference. Okay, and otherwise the goal, like before, is to satisfy as many clauses as possible. So what I put on the left here is for k-sat, for various values of k, the approximation ratio we got. So we really got 1 minus 1 over 2 to the k, which plugging in for different values of k, 1/2 or 3/4 or 7/8 is what we focused on, 15 over 16, 31 over 32. It gets better for larger k, right? The logic was just you have to get kind of all tails on your coin tosses to get a clause wrong. Okay. What approximation ratio would our oblivious algorithm get for a max-sat problem? Now you have a bunch of various different k's for different clauses. Okay, so if the clauses could have any number of variables and stuff like that, and we ran the oblivious algorithm, what would be my approximation ratio? In the worst case. Okay. So in general, what's the minimum value of k? 1. So our oblivious algorithm, we can't really promise anything better than 1/2 for max-sat, which is not so great. And this is what we want to address. And of course, this is already absurd, right? Because at some level, we're getting killed by clauses that have one variable in them. And these should not be the hard clauses to satisfy. Right? But somehow the possibility of this trivial thing hurts us. All right, so let's try out this general approach for max-sat. And here we'll do our first exercise of modeling an integer program. So I've set it up a little bit so that you guys can fill in the rest. In particular, I've already chosen the variables for you. So we'll have one variable yj for each variable xj in the formula. Okay, so I have an integer yj. And you'll also want a variable zi to indicate whether or not you're satisfying the clause. And I'll let you guys figure out how to be creative and put it together. So we need two things. At the top, we need an objective. What are we trying to minimize or maximize? Should be a sum of something. And then what are the constraints? What do the z's and y's have to satisfy?
Objective is straightforward, right? Since each CI is a clause, I satisfy and want to maximize the sum of CIs.
Okay. We want to maximize the sum Okay, so we want to maximize the sum of zi's, which says I want to maximize the number of satisfied clauses. Okay. All right, now we need to come up with some constraints, because obviously if there's no constraints, I would just make zi equal to 1 everywhere, and that wouldn't be very interesting. So what I did was I set up maybe one example of a clause here, and we can maybe try to think of a constraint. At some level, I should only be able to set z1 to be true if I've chosen the yj's so that either x1 is equal to true, or x2 is equal to false, or x3 is equal to true. Yeah. Okay. Yeah, so for us they're y's, but yeah. So corresponding to x1 is y1 plus 1 minus y2 plus y3 is greater than or equal to z1. Okay, so if I set x1 to be true or y2 to be false or y3, then this will be at least 1, and then I'm allowed to set z1 to be 1. And of course, any optimization program will make it as big as possible. Okay. Great, so if I were to generalize that for clauses in general, say the ith clause, we would be doing like, oh, I'm going to sum over, let's say all the variables j where xj appears as is in CI, so abusing notation a little, yj plus the sum over all j's where the negation appears, 1 minus yj, and this has to be at least our indicator variable for the ith clause. Okay, so yeah, so it's not too hard for most cases to model some combinatorial problem as an integer program, especially once you've done a few. Great. Any questions? Okay. So this is the same thing. It's copied over or done in advance. All right, now we want to get a linear program. So this is the integer program from before. I haven't changed anything. How do I turn this into a linear program? Yeah, so instead of saying y has to be 0 or 1 and z has to be 0 or 1, I'll say it's any value between 0 and 1. Okay, that's it. Not much to it. Great. But with that little trick, I now have something that I can at least solve with a computer. Okay. Original problem, solvable problem. And one thing to point out, so anything that's a feasible solution here, any valid set of y's and z's, is also valid here. An integer thing is a fractional thing, but not necessarily vice versa. Otherwise, the objective is the same, the linear probe. So consequently, the objective value on this side is always at least as good as the objective value for our original problem. And that's really important because we're gonna get an optimal solution, and we want to And when we turn it into an integer solution, we're going to relate it to the original value of the LP, which we know is very good. Great. Great. Okay, so now then here comes then the interesting part. All right, so I have already put it into my black box. I get the y's and z's. We're really going to focus on the y's because they're sort of suggesting whether to set variables to be true or false. So I want to take my y's, which are fractional values, and turn them into true-false assignments. You should put an n in the top right corner there. So I want to take my continuous fractional stuff and turn it into an integral thing. Okay. Any ideas? Oh. For a single variable, try to see how many. Oh, but that has nothing to do with the LP even, right? That would have applied originally? That's like a greedy algorithm for SAT? Okay. Yeah. Yeah. Okay, so deterministic rounding, right? Uh, okay, so those are two, but they're both rounding ideas. Okay, so just to restate hopefully correctly. So let's say you're looking at y1 equal, well, maybe 1/2 is right in the middle. If you have like y1 equal to 3/4, you might be thinking, oh, that's closer to 1. Then 0, I'll bring that up deterministically to 1. And if I had something very small, I'll bring it down to 0. And maybe 1/2, I'll decide to round up or something. Okay? Mm. Okay, so for the deterministic one, I think maybe one counterexample might be the following. If I had, imagine I have lots of clauses with lots of variables. Something like that. Something that would satisfy this clause in our LP is if I had set all of these to be a small value but adding up to 1. Something like that. So with large clauses, the LP might want to, because it can sort of fractionally divide up how to satisfy each clause. So the LP could very well set very small values to everything, but satisfy many clauses. I could imagine that happening. In which case, deterministically, everything will be sent down to 0. I didn't have to choose 100 to even make this point. I guess 3 would have been fine, right? But it will send everything deterministically down to 0, and you just won't satisfy anything. Okay, so while that makes sense, I mean that's the most this is always the first suggestion. It seems a little tricky. Okay, so another thing is, okay, so we're going to get to a second point, but let me do the annoying teaching thing. So at some level, let's say the LP tells you you should set y1 to be 1/2, and how do we interpret y1 to be 1/2? At some level, it's saying, oh, it should be half true and half false, right? Which at some level makes no sense. Something cannot be half true and half false. Okay. Well, I guess I can make jokes about politicians or something, but that's besides the point. Okay, so but in the randomized algorithms class, how do I interpret something that's half true or half false? Or how do I interpret something that's half heads or half tails? We're saying that half the time is true, half the time it's false. Okay, so one thing I think very important going on in randomized algorithms and randomization in general is it gives us a real way to interpret fractional values in a discrete world. Statements like half true, half false make sense if we mean half the time is true, half the time is false. Okay, so that's what we're actually going to analyze. So when y1 is equal to 1/2, we're going to flip a coin. If it's heads, it'll be true, set to true. If it's tails, it'll be set to false. If the probability, if it was like 3/4 or something, it's going to be true is probability 3/4, false is probability 1/4. All right, so this is what we will analyze. Okay. All right, so, okay, so that's good. All right, so now the question is, how many clauses will we satisfy an expectation? Okay. Okay, so, all right, so now, here's the claim. The claim, we'll just focus on some particular clause CI. It could have been the first clause. We're claiming that every clause is satisfied with probability 1 minus 1 over E times the value assigned to it by the LP. Okay, so ZI was whatever the LP said. All right. So, so we need to analyze this. Let's start. All right. So the probability that CI is satisfied. Okay. So how should we get started? How do I analyze this? Yeah, we are looking at one clause. Yeah. We're just looking at some CI. So what should I do with that one clause? Yeah. Okay, so we need one coin toss to come out in our favor, and which means sometimes it's actually easier to analyze the probability that CI is not satisfied and upper bound that. Okay, so what is this equal to? I guess it's a little bit wordy, but we can, we're looking at the product of all variables xj in the clause, and it needs to come up tails. So that's 1 minus yj. This is the same as before, just notationally a little bit heavier. And I guess we have different probabilities. Okay, it's yj. So this is the probability of all the coin tosses going against our favor for that clause. Obviously, this is a mess. So how can I clean it up analytically? Yeah. We have the constraint in the linear program. So we know that the y's are ultimately related to the z's by this equation. But there's an obvious difference, right? Which is that this is a product and this is a sum. At some level, my feeling is that products are hard to deal with. Sums are always easier to deal with. How do I turn products into sums? At some level, this is like what makes all of our probability problems a nuisance. Log. Well, that's true, but I'm not allowed to just take logs of stuff for no reason. If I did take a log, then you would get, some sum of log of 1 minus yj's. plus some log of sum of logs of yj's or something. Now it's hard to relate this to that because you have logs around everything. So that's still an issue. Right? So how do I get from a multiplicative mode into an additive mode? You guys have done this before in previous classes. We do the only thing we know how to do. We use that inequality, okay, which is very similar in spirit to your log idea. But the basic idea is that when I exponentiate the product of exponentials, now you can sum up the top right corner, right? So less than equal to e to the, well, maybe I'll do one step at a time. Product e to the negative yj. Okay. How do I deal with the other one? Because yj is not of the form 1 plus x. Yj is equal to 1 minus yj, I think. I got that right. Okay, this looks just as ugly as before, but now why is it nice and easy, more friendly? I see some hand waving, but I'm the only one allowed to hand wave when I ask questions. Yeah, but help me get there. How do I make it look like the LP? Yeah, why does it merge? Okay, get this. E to the negative sum. I'll put it negative sign. Sum it. Even if you can't read my handwriting, hopefully you can guess what I intend to write. Okay. So in the top right corner in the exponent, now I have something I know how to work with. This thing is at least zi. Less than equal to e to the negative zi. Oh, this came out a little different than I had expected. Oh no, it's okay. We're only one trick away. All right. All right. Okay, so this is just a little bit of math left. I want to go from e to the negative zi to 1 minus 1 over e zi. Okay. So, trying to think of a hint. Can't think of a hint. Can anyone want to take a stab at it? All right, that's all right. So, in general, the function e to the minus x is a convex function. Okay, so, all right, so, okay, so what do we know about convex functions is that oh, am I doing something? All right, let's see what happens. Okay. All right, so, okay, so at some level we have 0, we have 1. Here I have e to the negative zi along the red line. And up here, we have zi times e to the 0 plus 1 minus zi e to the 1. Did I get that backwards? Okay, so let's write that out. E to the negative zi is less than equal to e to the 0 zi plus 1 minus zi times e. I'm only putting the 0 and the 1 to remind ourselves we're using convexity, but of course. Okay, so that's zi plus 1 minus zi times e. Oh no, it should be minus 1, shouldn't it? Okay. All right, so what does that give us? This gives us e to the minus 1. Did I get this backwards again? Okay. Sorry. All right, this seems to be what we got. Did I do something wrong? Yeah. That's what I wrote in my notes. Okay, let's do it the other way. See what happens. Okay, good. We're okay now. Okay. Does that seem correct? Great. That was all the probability that CI is not satisfied. So if I want the probability that CI is satisfied, we'll do 1 minus that. All right. Sound okay? I found a typo in the notes, so that'll be fixed. Okay. All right. Okay, so every clause is satisfied with probability 1 minus 1 over e times zi. So now the next step is to relate everything to opt. Okay. All right, so how do we do that? Yeah. All right, good. Linear expectation. So this thing is equal to the sum over all the clauses, the probability that CI is satisfied, which we've now shown to be at least the sum over I, 1 minus 1 over E, Zi. Now here's the last step. The last step is important. How do I get to opt? Yeah. Okay. Perfect. So the key point is that we know that the z's are actually really good. The z's from the LP are at least as good as any integral z. So that reference point is the only reason this thing comes together. Okay. All right. What comes next? All right. So any questions up to that point? Great. Yeah. That's right. This has nothing to do with the number of variables in every clause. It's also a little bit more magical then our first algorithm where we randomly flipped everything, we knew exactly why we got 7/8, right? Here at some level, who knows what's kind of going on over here? I just assume it's optimal, and I relate to the optimal solution given from the LP. But the LP may be doing lots of clever things, kind of looking closely at the clauses. So there's something structural, something that depends on the formula going on here. Although this, once we get to this point, there's not much to do with the formula anymore. All right, so the next fun part is trying to do a little bit better than 1 minus 1 over e. How are we going to do that? All right, so we showed that every clause CI is satisfied with probability 1 minus 1 over e zi. Right? I think we showed it. It was a little clumsy, of course. All right, but what if clause I had one variable? In that special case, what would the odds have been? Yeah, it would have been zi, because there would have been one variable that would have been equal to zi. It would have been zi. So this bound of 1 minus 1 over e zi is not particularly good for the special case of one variable. Let's also look at two variables. So this is not as obvious. We'll have to actually work through it. All right, so let's say that we had, for example, C1 was, say, the union of two variables, x1 and x2. So the probability, I'll call it Ci, the probability that Ci is not satisfied in this case would be 1 minus y1 times 1 minus y2. Now last time we were lazy and we went straight to our only inequality like that. But here we're going to do something a little bit sharper to get a slightly better bound. Okay. Does anyone have any tricks for bounding the product of two non-negative or two positive variables? AMGM. So AMGM is something like has to do with like you have some fence and you want to cover the most area. Okay, so what would AMGM actually be? AMGM is like A times B is less than equal to A plus B over 2 squared. Okay, so if we use that here, we get less than equal to, see if I have enough space, less than equal to 2 minus y1 minus y2 over 2 squared. Okay, great. Anyone want to suggest something to do next? In particular, we might be able to bring z back into the picture. So what's y1 plus y2 equal to? Wait, what? Can one person speak a little louder? A z, okay. 1 minus zi over 2 squared. Okay. We're going to do the same convexity trick. 1 minus x squared is also a convex function, or 1 minus x over 2 squared is a convex function. So this will give us 1 minus, looks like I found more typos, 1 minus zi times the value at 0, 1 minus 0 over 2 squared, plus zi 1 minus 1 over 2 squared. So this is just because the function f of x is equal to 1 plus x over 2 squared is convex, just like the e to the stuff before. It's going to look something like that. Okay. And then I guess if we work this all out, get something like 1 minus zi plus zi over 4, which is equal to 1 minus 3/4 zi. Okay, so that was a probability that Ci is not satisfied is 1 minus 3/4 Zi. So the probability that Ci is satisfied is at least 3/4 times Zi. Okay, so 3/4 is actually bigger than 1 minus 1 over E. 1 minus 1 over E is like 0.68 something. Okay, so we get a better bound for this case as well. All right, so one second. Rats, I can't cover it up on the screen. Oh well, doesn't matter. All right, so what I've made 3 columns here. The first column for a particular formula is, or for a particular clause is from the oblivious one, right? 1 minus 1 over 2 to the k. And the next column is how many points we are getting from the LP in expectation. So for all of them, we get at least 1 minus 1 over e, but for the first 2 special cases, we got slightly better bounds of zi and 3/4 zi, right? And what's sort of interesting is that if you average these two for any row, you get at least 3/4 zi. So the first column, 1/2 is at least 1/2 zi. So the average will be at least 3/4 zi, and so forth. Okay, because zi is at most 1. All right, so what I'm saying is that we have 2 algorithms. And it feels like their average, sort of on a per clause basis, would give us a 3/4 approximation. But we don't actually have an algorithm that gives us a 3/4 approximation. This is just suggestive. So the question is, how can I combine somehow the 2 algorithms and get a 3/4 approximation? This is a fun one. I'm going to give you guys a chance to think about it. I'll note that the algorithms are almost completely opposite. One algorithm is completely just flipping coins. And the other algorithm studies the LP and does quite a lot of optimization under the hood based on the structure of the formula itself before we round. So this rounding algorithm highly depends on the formula. This one is completely oblivious. They feel very opposite in personality. Yeah. So it would be great, for example, if I can on a clause by clause basis be like, oh, this is a big clause, I'll use the random oblivious one. Oh, it's a small clause, I'll use this, right? But we can't necessarily do that because these clauses share variables with each other. So it's a little bit hard to be selective about, I'll do some like this and some like that. Because in general, the whole point of these combinatorial problems is all these interdependent connections. Yeah. Yeah, is there any way to figure out which variables to do obliviously and which ones to do? Like, let's say just start with x1. Oh, but this starts getting back to the original greedy algorithm. That almost has nothing to do with the LP either, right?
I think so. Both the oblivious algorithm and the LP algorithm are not deterministic, right? Like we run
Uh-huh.
multiple times to get different solutions. What if we run, say, like both of those algorithms like 10 times each and then pick the max out of the 20?
Okay. So why not run both algorithms 10 times each and take the best? Why not? Um, so my concern though is that the best you'll get from your oblivious one is uh, say 1/2 because there's some one clauses in there, and the best you get from your LP one is 1 minus 1 over e. So you just end up with 1 minus 1 over e. Yeah, average 2 runs and then round. Uh, just throwing all the words we can think of in there. Okay. Uh, guess why not? But I can't see why it would work better. All right. Probably not, but I'm not sure why not. Give up?
What if for each variable x, we give it a 1/2 chance where we sample it using yi, and a 1/2 chance where we sample it universally at random? So basically, each variable xi has a 1/2 chance of getting the value it would get from the LP
Okay.
algorithm and 1/2.
So on a per variable basis, try one of the two strategies. Okay. I'll only suggest that in the analysis, it'll get a little bit complicated. Well, to some extent, the reason why the LP approach worked or something was, for example, we knew that all the yi's would add up to the zi, or all the yj's would add up to the zi's. If you take out half of them, you're guaranteed something get weaker. This might be replaced at least by zi over 2. All right, I'll just reveal it then. All right, so here's what we're going to do. It's at some level implicit in some of the suggestions. All right, so how do I somehow get the average performance of two algorithms? In particular, I want to get the average of their average performances. We're just going to flip a coin and then choose one of them randomly. Okay. All right. So the claim now is that each clause is satisfied with probability 3/4 times zi. Okay. All right. Does anyone see why this is true? So for a particular clause, let's say we're in this row. If I flip heads with probability 1/2, we'll get 15 over 16. If I flip tails with probability 1/2, I'll get 1 minus 1 over e. Zi in expectation, on average, I'll get at least 3/4 zi. That's true for every clause. So, I mean, conditional. So 1/2, 1/2, doing the conditional stuff. Hopefully no need to do it out. All right, so by doing this half and half strategy, again, in our randomized interpretation of half and half, we are able to get the average without actually having to literally mix the algorithms, right? So the original analyses are completely separated still from each other. This is obviously very lazy. We don't have to do very much. I don't even want to write out the proof of this claim, right? But it works. But it's really leveraging the fact that we're only interested in average performance and stuff like that. All right, so any questions? That's how we get a 3/4 approximation.
Can we balance you say we pick one of the two algorithms with the 50/50 chance, right? But then wouldn't that always be bounded by the max of the two?
Yeah. So now in hindsight, the suggestion of actually just running both also would have been fine because you can just take the better of the two. But this will give you you need to do this to prove it. In fact, one of the homework problems will be also to de-randomize this. So you don't even have to make any choices like that. Okay, great. All right. Okay. Okay, so we probably won't do covering integer programs, but I hope we can at least discuss set cover. So I'm guessing you guys might have seen set cover before. Sometimes it's treated as one of those introductory empty hard problems. But it's a combinatorial problem. So you have m points in some space and n sets of points. And I want to choose the smallest number of sets that covers all the points. Okay, so this just comes up all the time in kind of resource allocation type scenarios, but here it's just abstracted to its mathematical bare ingredients. All right, any questions about the problem? Fair enough, it's NP hard, it's one of those original NP hard problems. Let's write an integer program for set cover then. I've already chosen the variables for you. Xj is 1 if I'm going to put the j set in my set cover, and 0 otherwise. So what is the objective? There's no time left to be shy. What is the objective? Sum of xj's. I want to minimize the total number of sets I take. Subject to every set sums to over 1. Very close, but just switch some words. Okay, so for every point, I need to cover it. So if I sum over the sets that contain the point, so I'll just make up some notation. Sj contains I. Xj, this needs to be at least 1. I need to take at least set that covers that point for every point. All right, simple enough. This is actually simpler probably than our last one. Okay. How do I turn that into a linear program? Just change it. Okay, nothing special there. But suddenly we get to use this unbelievable black box. Same point as before. One of these we want, one of these is solvable. Great. All right, here comes the fun part. The LP gives us a fractional set cover, so to speak. I want an integral set cover. How might I round it?
Question. What is our objective here? Do we want to always get a correct set cover, but it might use more sets than...
That's right. Okay, so when we do approximation algorithms, we always want to satisfy the constraints and approximate the objective. So in this case, I want to make sure that I do cover all of the points, but I'm allowed to take some extra sets. Yeah. Okay, so how might, yeah? Okay, so what we did kind of last time, I mean, the corresponding thing was for a set Sj, I'll take it was probability Xj then. Okay. So let's work through some simple calculations. So this time I'm interested in two things. Last time I was just interested in how many constraints I satisfy, but here we have to satisfy all the constraints, and then I'm also interested in the objective. So there's a little more going on. So what's the expected number of sets I take? Yeah. Okay. So by linear expectation, each set is taken with probability xj, and this is equal to opt. Is the from the LP, or is less than equal to opt. All right, fine. That's not the hard part. Here's something more interesting maybe. If I look at a particular point I, what's the expected number of sets that we take that are covering I? Or how might I go about it? So we'll sum over all the sets that contain I, and what's the probability of that set appearing? Xj now. Sorry, I switched on you. You had it the other way the last time. Xj, and this is at least one. Okay, so that makes sense. So what the LP is sort of saying is that in the randomized rounding, the expected number of sets covering it should be at least one. That kind of makes sense. Fine. But that's not really what we're interested in. We're interested in what is the probability of I being covered. Okay, so let's look at the probability that F does not cover I. And you said, oh, we can do something like last time. So we can take the product over all the sets that contain it, 1 minus xj. So if they all come out tails. And in here, what do we do? Xj. And since they all sum to at least 1, you get something like that. Okay. So we cover I with constant probability. Great. All right, so, okay, what did we show? I guess we showed that we have very good objective value, and we cover each point with constant probability. So now we have a set cover with constant probability, right? No, that was a trap. That's wrong. Okay, so just because any particular point is covered with probability I does not mean we cover all the points. Or sorry, any particular point I is covered with constant probability. Does not mean we cover all the points with any significant probability at all. Okay, so this is okay, not true. Okay, so that's sort of the issue here, is I need to figure. I'm really interested in what are the odds of covering all the points simultaneously, and I want those odds to be high. All right. So faced with this quandary, what might we do? Yeah. Okay, so this is not a bad idea. So you're hoping that you're covering a constant fraction, and then so you get rid of half the or some fraction of the points, and then just do it again, do it again, do it again, and you're hoping that in logarithmically many rounds you'll kill off all the points, and each time you're paying opt. This will work, but the next slides don't talk about this approach. Okay, so that's one way to go about it. What's another way? We're going to try to do it another way that doesn't resolve the LP. We're just going to stick with these x's and try to finish the job now. Yeah. Oh, that's true. I could even actually reuse the same x's again and again. Okay, that's the second algorithm I wasn't prepared for. Okay, good. But that's similar to the first idea. Uh, okay, but another thing is, okay, let's see what I wrote. All right. So we're going to try to take this approach and sort of put it on steroids. So instead of flipping heads with probability xj, maybe I'll multiply it by 100 first. So the odds go up by a lot, and then I'll flip the coin. We'll figure out what alpha should be at the end, which must be soon. All right. Actually, we'll get the same bounds as the other approaches that were suggested, but still it's good to do it in different ways. All right, so the expected size, I'll cut to the point. We're just paying an alpha factor bigger than before. Everything went up by alpha. Okay. Now look at the probability that we don't cover a particular point I. We're going to be doing the same calculations as before. Let's assume that alpha times xj is smaller than 1 for all of the relevant j's. Otherwise, you're definitely taking a set covering the point I, so there's nothing to analyze. Okay, so taking the product, 1 minus alpha xj, and do the same thing as always, except we have an alpha there now, sj containing I, xj, which is equal to e to the minus alpha, right? So this is exponentially small in alpha. That means I only have to increase alpha by a moderate amount and really drive down the odds of messing up this point. Now if I want to look at the odds of covering all of the points, how might we do it? What's the first step? Union bound. Okay, summing over all the points, what are the odds of not covering that point? So this is m times e to the minus alpha. If I want this to be something really small, like 1 over m squared, say, that would be great. What should I make alpha? Yeah. Yes. Also known as 3 times the natural log of m. Right? So but the real point is I make alpha roughly log m, which is actually like before, you guys also repeated your algorithm log m times, you get the same factor. But if you do alpha equals 3 times log m, then e to the minus alpha will give you 1 over m cubed times an m. Okay? So we get the same trick that always comes up. Once I exponentiate, I have so much leverage that I can easily take union bounds over all the things I'm interested in. Okay, so all we did was just put it on steroids and that's it. So overall we get a logarithmic approximation for this problem. So that time you just had to increase a little bit. Okay. All right, so I'm not going to say too much about the last thing. All I'm going to say is that whereas set cover was like a very simple kind of 0, 1, cover it or not, okay, you could have a slightly more general form where you have covering constraints. You want the sum of something to be bigger than something, just like you wanted to take at least one set covering a point. And you can have things like cost. So this is just generalizing set cover. Okay. And roughly we can do the same thing. We can scale up and randomly round. The only thing that'll be different is that this calculation will be a little bit more complicated because it's not this nice yes or no. So before with set cover, we're just worried about what are the odds of not getting any of the sets, the odds of getting all tails on the coin tosses. Whereas this needs to sum up to something bigger than that. Okay. So the only thing we would do that's different is that there we would use that turn-off bound from last time about sums being concentrated. Okay, so if we scale up x so that this sum is like 100 times bi, then the odds of, when we randomly round it, of being smaller than bi will go down really fast. Okay, so that's the only difference, is we swap out this calculation with turn-off, but the same otherwise high-level ideas will apply. All right, I know I went over. I'm sorry about that. Thank you.